All right. Now I'd like to welcome our next speaker, Miguel Palencia. Palencia. He's with Lenovo, and all the hardware that the previous speaker spoke about. Miguel will probably tell us how you can architect it for even more genomics problem-solving solutions. So I'd like to turn it over to Miguel. Miguel, go ahead.
Yeah, hello, good afternoon. So my name is Miguel Terol. I'm HPC and AI architect at Lenovo, and I'm glad to be here today. So thanks the organization for inviting us for this specifics. And yes, in fact, it's a very hot topic. How we can leverage our systems and how we can tune our systems for better performance in genomics analytics, but not having to spend a huge amount of money, which sometimes it's the blocking factor for progressing in research. So let me first introduce a little bit what we are doing in the supercomputing scenario, in the supercomputing arena. So many of you may know that Lenovo is currently the number one provider of supercomputers in the top 500 list. So more than one every three systems is manufactured by Lenovo. So, this slide, beyond being a nice marketing and a nice publicity for Lenovo, it does for me show really the capacity of delivery end-to-end supercomputers that Lenovo has from not only the servers, but also networking as high-performance storage. But not only that, but also HPC services, system tuning, and the design of the solution itself. So it's always in collaboration with our beloved customers. So one of the things we like most is to collaborate with our customers. So many of the top research universities run Lenovo systems, and it's not because we can offer a better price or a better price performance, but because also we collaborate in the design of the solution with our customers. So we will put some examples later on how we collaborate specifically on the life sciences and genomics analytics. But talking about more specifically genomics analytics, so what can we do? What are we doing to help you deploy your life sciences, your bioinformatics analytics at a certain scale without having to spend a lot of budget? Okay, first of all, we identify the workloads in bioinformatics, which is biomedicine plus some HPC systems, with the workflows of the genomics analytics. But not only that, also some other workflows such as transcriptomics or molecular dynamics or any other thing like that. That we have identified to be highly sequential many times. And we want to address them all, not only the genomics analytics. Let's see how we address this. And first of all, we have identified what the challenge is. And if you're a bioinformatician or a user of genomics analytics, you may have found out this bottleneck many times. So to get a genome sequenced and analyzed and processed, there are several steps involved in that, from the extraction of biological samples such as blood samples or skin tissues or something like that. So we extract those biological samples, and through specialized hardware such as a sequencer, we get some readable data, and some sequencing readable data that can be then processed by a machine to get all the variants and all the data needed to compare to genomes or get the variants calling. So this is the largest bottleneck, taking up to 150 hours to get one single genome sequencing process. So having identified this, and of course, this means a big problem when trying to get results. For instance, let's imagine that a certain research lab is wanting to design a treatment for COVID-19, addressing the different symptoms that a patient may have. Some of them present pneumonia, some of them present just mild or no symptoms, and the research lab wants to know what the difference in the genomes of these two persons are. So what does it mean? The more sequences they get, the more genomes that get them sequenced, the more capability of producing relevant results they're going to have. And if for each whole genome sequence, they can take up to 150 hours or at least 40 hours, doesn't matter. That impacts a lot in the ability to get papers published or get some grants or produce some relevant results that at the end will be used to produce a certain treatment. Okay, how to alleviate this bottleneck? One way is to use a specialized hardware or more complex hardware using certain accelerators such as GPUs or FPGAs that also need some software that needs to be tuned and adapted, and that means licensing fees. And at the end, it means an increase of costs that many research labs are not capable to afford. Plus, getting for genomics analytics a specific architecture if they want to run some other workloads such as transcriptomics or cryo-EM or something like that, they will need to purchase a separate hardware. All right, something similar occurs, for instance, for a pharma company that is trying to design a new drug with fewer side effects or some other functions, and they find exactly the same problem. So they need to sequence and analyze the sequences of as many genomes as possible at a population level. So again, this is the bottleneck they are finding. The more time they spend trying to find this drug or get those sequences analyzed, the more time to get some profit, and profit not only in terms of financials, but profit in terms of, for instance, time to market, availability to the population. So again, they also face the same problem of having to spend a lot of money and perhaps not being capable of affording that. So I would like to talk about our approach to this solution in order to alleviate the bottleneck, get a better time to results without having to spend a lot of money on specialized hardware. First of all, how have we done this? Okay, our teams of experts in architectures for life sciences have been trying to find a way to design a certain hardware and software configuration with an open architecture, that meaning not having to use very fancy or expensive hardware pieces such as accelerators. And this team have been doing a study of permutations of the different factors that may affect the final performance of the variant calling workflows using JATK as the most popular open source tool. So with different processor combinations, different internal storage options, also testing different memory configurations and the amount of sockets, the socket count inside each system, trying to find the best and the optimal configuration without having to spend a lot of money. The premise, of course, is no software, no code level changes. That means the software stays as it is and does what it has to do. And that meaning a regular JATK distribution can be used for this, but only tuning the runtime parameters with many different options. And by using this, also they have configured the runtime the runtime, about the number of threads that can be executed at a certain time and things, but without having a single code of the software, the functionality of the software itself. Plus some internal hardware system tuning, such as changes in the UFI codes or certain configurations for better performance or energy efficient or something that can be tweaked inside the machine itself. Okay, so the outcome of this thorough study has been a solution, a hardware and software-based solution. Oops, sorry that my clicker is not working properly. Let's see. Okay, sorry. Okay, so the outcome was the Lenovo GOAST solution. GOAST, that stands for Genomics Optimization and Scalability Tool. It's the specially tuned hardware, as mentioned, the outcome of this study that we have performed in our labs, plus the pre-configuration of the JATK software to maximize all the resources that we have defined before. So these configurations that we have found in two different flavors, let's call them Lenovo GOAST Base and Lenovo GOAST Plus, being Lenovo GOAST Base kind of a price performance oriented solution for this genomic analytics workflow. And the other configuration, it's an 8-socket system. It's the Lenovo GOAST Plus oriented to performance. Still affordable, but oriented to performance. So what's the difference between the both? Well, first of all, let's talk about the performance of the first one, the Lenovo GOAST Base. In a dual socket configuration, we have compared with the publicly available results from other competitors that have already taken their time to optimize their own systems. And we have found that we outperform those systems by taking up to 3 hours to get a whole genome sequence processed. This is with a regular dual socket configuration. If we go to the performance-oriented configuration, the 8-socket based Lenovo GOAST Plus, we indeed find that the time to result decreases dramatically up to only 18 minutes. That meaning that you can process a lot of genome sequences every day, and having the time to results much sooner than with any other solution. That's also in line with some other specialized solutions such as Illumina Dragon or NVIDIA Parabricks that are making use of those FPGAs or GPUs or accelerators with specifically tuned software for this genomic analytics, and also having to dedicate this architecture specifically to genomics analytics. Our solution is also intended to provide support for many other life sciences workflows, such as molecular dynamics or cryo-EM, because it's an open architecture, a CPU-based architecture. All right. So we see the increase in performance. We see a faster execution with both options, and of course, GOAST Base is a cheaper solution than GOAST Plus, obviously, because it has a lesser configuration. We will see the configuration later and on a slide. And it's more affordable because it's a purely CPU-based and no software licenses is required because we are using regular JATK. It's easier to use because we ship it already configured from the factory, or it can be optionally configured on site if the user wants to. And we have a secret recipe, of course, but there's no magic in it. I mean, the secret recipe is our own hardware and system optimization that was the outcome of this hard and long work that we have taken. And by the way, it's a work in progress. That meaning that it never stops, and we are always trying new combinations to even reduce to a faster time those time to results. All right. Those are the two configurations. As said, Lenovo GOAST Base is a dual socket system, ThinkSystem SR630. In fact, the system model doesn't matter too much. That means that we could go to another form factor, but with the same tuning parameters that we have implemented in our Lenovo GOAST Base. It's a dual socket with 384 gigabytes of RAM with local drive or local SSD up to 2 terabytes. With this, we reduce up to 3 hours the processing of the whole genome sequence. Lenovo GOAST Plus is maybe not that cheap because it's an 8-socket system with 1.5 terabytes of internal memory and 4 terabytes of local NVMe drives with optionally a network high-performance storage option. That is also possible, depending also on the functionality and the data flow that we are expecting from our own data, meaning the data to be analyzed will be residing somewhere in our network, and we will have to move that data to somewhere where these systems can process these workflows. And those were configurations that allows you for a certain committed performance. That meaning, if we say that you can run a genomics a whole genome sequence of 30x processed in 3 hours, we commit to that. But or in 18 minutes with GOAST with a GOAST Plus solution. But that doesn't mean that you are limited to that machine. I mean, you can scale. And as most of these workloads are sequential, you can increase your performance. I mean, the number of genome sequence per day or per or per week or whatever your time metrics is, linearly by adding more nodes to that. But sometimes things are not that easy, and maybe the conjunction of circumstances are another story and specific for each customer. Well, that's why we have internally our own sizing tools, and we can advise you depending on the amount of data you will need to process every week or every year or every month, and the amount of genomes you have to sequence, depending also on the density of the sequences, and or whether you want to do some exome sequences instead of genome sequences. We are here to advise you on the best way to deploy your scalable architecture. So that meaning that you will optimize your budget in order to get as an architecture as scalable as possible within your existing budget. Okay, we have some success stories around the world. In many both public and private institutions of very high prestige. One of them I want to mention is our beloved customer, Barcelona Supercomputing Center, which is not only a customer but a collaborator. In fact, we are collaborating in many research lines, being one of them the optimization of the pipeline of genomics analytics. So partly the outcome of the study that we have performed on our own systems have been taken into account our collaboration and the results of the collaboration with Barcelona Supercomputing Center. Also, for instance, University of Delhi and the Department of Genetics that is doing some kind of nice use case that I will present in a slide right after this one, and some other prestigious institutions all over the world. Being one of them, for instance, University of Birmingham, with which we won. In fact, University of Birmingham won the HPC 2020 award for best life science solution using our GOAST solution, and some other prestigious institutions all over the world. A curious case, and that's why I wanted to mention in this presentation, is the University of Delhi, uh, which are doing this deep sequencing and de novo assembly, but they are oriented to agriculture, to plant genetics. I mean, not everything, and of course, is very important, the healthcare, but healthcare at some point in time also touches what is the food care and also the health of the agriculture and many other aspects. So this is very interesting that we are collaborating also not only in healthcare but in plant genomics. So trying to summarize, our goal is to provide not only a genomic solution, but a solution that you can use for any bioinformatics workload. Not only genomics and variant calling and de novo assembly, but phylogenetics, molecular dynamics, proteomics, and similar things, because we don't want you to limit your architecture, that the system you purchased from Lenovo, we don't want it to limit you to the use of genomics analytics. So it's an open architecture. You can use it for anything else that you might be wanting to. So again, do not hesitate to contact us, because we can specifically size your system, your architecture. We can advise you so that we can only we just let you do your work, which is produce research results. I mean, we are caring about the results themselves, about the infrastructure, and the researcher cares about the results without having to care too much about spending a lot of money or having to tune by their own their systems. And well, that was it. So the intention was to show you how to best use your available budget. The intention is to let us know how we can help you, and to show you how we are really helping many of our customers by using an open architecture with open source software, and taking care of your time to results and your budget. So that was it from my side, and I really appreciate your time. And also, if there is any time left, I have been trying to get on time. If there is any time left, I will be glad to answer any question if there is any.
Yeah. Thank you, Miguel. That was very, very informative. You have contact information there. There are no questions I see right now, but I'm sure there are a lot of people involved in the genomics world who, yes, would like to focus on their problems. And if you make it easier for them, that'll be welcome. Thank you, Miguel.